So welcome students to this live session on this course called the Advanced Quantum Mechanics with Applications. As you have felt that the course deals with somewhat advanced topics in quantum mechanics, including the ones that are somewhat elementary and fundamental. We have touched upon those as well, but also have gone to talk about quantum information, quantum cryptography, a little, not too much. And then we have gone and looked at the approximate methods in quantum mechanics, which formed a good part of the later part of this course, which you are being exposed to. Advanced quantum mechanics usually is a course for senior undergraduate or the postgraduate classes or students who are interested in learning how quantum mechanics can be applied to various real life problems, and a large amount of it, the large portion of it, is dedicated to solving problems that are important in various fields, mainly the quantum mechanics, nuclear physics, atomic, molecular, and spectroscopy. And of course, as we have seen, a little bit of quantum mechanics, quantum information. So it's by and large a course that is completely dedicated towards an in-depth understanding of quantum physics that is taught in the universities at the senior undergraduate level. So I'll be happy to answer some of the questions that you may have. And there are some questions that have already been told, or rather have been put up by some of you. And these questions are, first let me take these questions, and then you can also ask other questions if you have. It says that comment on the normalization constant of multi-electron systems. It's important to understand that a multi-electron wave function is actually written in terms of the Slater determinants. And these are basically determinants. So these things are written in the form of determinants, because interchanging any rows and columns would bring about a minus sign, which is inherent, and it's actually embedded into the antisymmetry property of the fermion wave function. And the normalization is done in the same way that it is done in normal one-particle quantum mechanics. It could involve the number of particles, or the n factorial of those particles, and would take into account it's basically a properly normalized Slater determinant. And at this moment, the amount of things that we have considered, we have mostly talked about one-particle quantum mechanics in most of our cases. So many particle systems haven't really been discussed or talked about. But the question is still a valid question, that how is the normalization defined in a many-particle system or a many-electron system? And that is, as I said, that it is still, the idea is still the same, that the mod square probability or the square integrable probability should add up to 1. And that's the condition that gives the normalization. So there'll be a factor that will come in front of the Slater determinant, and which are which is the normalization constant. And there are questions asked that what are the uses of advanced quantum mechanics? As I said, that there are a large number of applications that entail this course. See the NMR spectrum, or the NMR, the basics of NMR that has been taught. Those are used by all chemists in finding the chemical structure of various structures that they talk about. And all these structures that you know, long protein structures and all that, they have been found out by NMR. Quantum information and quantum cryptography are now becoming very exciting because of this possibility of the quantum computers being made, and the pace at which computation can be done, or by virtue of this inherent parallelism built into this quantum computation. So it's one of the main things about this course. And also, in various topics such as nano science, nanotechnology, semiconductor physics, and everywhere you go to small scale and try to build, fabricate systems, chips, as you go down in smaller and smaller scales, it becomes more important to have quantum effects to be considered, because the energy levels get discrete, and the effect of, so to say, H, which is the Planck's constant, starts showing up. And it's only then that the quantum effects become very interesting, and you cannot ignore quantum effects. And these are bound to happen in small scale systems. Miniaturization of various devices, such as the chip that you have in your mobile or in your computer, that is getting smaller and smaller. And that's why the sizes of this equipment, which we had seen 10 years back, and the ones that we see now, they are fairly different. And these are the reasons that this course gives you an in-depth understanding of a large number of physical concepts that are used. So this question that the qubits are, so we are talking about qubits. When you talk about qubits, you really talk about a two-state system, which we have emphasized over and over again. Semiconductors are materials which help you to make these qubits, but there's no one cannot say that they are how they are realized in semiconductors. Any semiconductor device which has an on-off operation, that is either a 1001 kind of operation, can be treated as a qubit. It's just like what we said, that it's a quantum bit. So it's anything, not only semiconductors, anything that has a 10 or a 01 structure, that's a binary structure, that just like a switch which has an on and off state can be used as a qubit, or a spin half particle can be used as a qubit because it has two states, and so on. Neutron protons can be considered as a qubit. So that those are the things that are important in the qubit, in the quantum bit. As per se, it has no relevance to semiconductor physics that you are maybe exposed to in a solid state physics course, but anything and everything that has this binary structure can be considered as a qubit. Let me take some more questions in between. So somebody asked this question that why do we use the radio frequency magnetic field to resonate nucleus in NMR? It's a good question because we need to understand that first of all, what's a radio frequency. So in NMR, just to remind you that there are two magnetic fields that are applied to a material, and one is a constant magnetic field, say applied in the Z direction, and there's another oscillating magnetic field which is applied perpendicular to it, say in the X direction. This is that the second magnetic field is being talked about, and it has a frequency of nearly 600 to 60 to 800 megahertz. So basically these are relevant, these frequencies are relevant for the energy, the spin states of this nuclei. And the spin states are the difference between two spin states are such that, so let's call that as delta E. So delta E over H is of the order of the frequency that you're talking about, nu. So delta E by H equal to nu, and nu is of the order of 60 to 800 rather megahertz. In clinical MRI, one is exposed to this MRI, which is used in many of the diagnostic techniques. It's called magnetic resonance imaging, where 50 to 80 megahertz, that kind of frequency is used for the magnetic field. So just to say that the radio frequency matches with the change or the difference between the energy levels of these spin states of the nuclei, and that's why the RF frequency is used. Dynamic mass of photon is something that photon is essentially it's massless. Okay, even if it's moving at the speed of light, it is massless. In fact, it's one of the questions that asks this P equal to H over lambda, or lambda equal to H over P. So the question is that what is the de Broglie wavelength of these photons? And so if I can write here, just give me a moment. So lambda equal to H over P. Now P for other massive particle, it's equal to say mv. However, for photons, we have to write down the energy momentum relation, which can be written as, for a relativistic particle, it can be written as m square C4, so square root of that. Now, for photons, of course, this term is equal to 0, so one gets a PC. We are not distinguishing between the plus and minus sign, which we can take care of later. So P equal to E over C. So this is equal to so HC over E. So it is still so that's the de Broglie wavelength. So even if the photon is moving with the speed of light, which we see here, c being the speed of light, it still has the rest mass is equal to 0. So there is no mass of photons that one comes across, and which is verified in experiments. All right, so there's another question. Let me take another question that says that due to current flow in a conductor, Is there any deficiency of electrons that occur? No, there's no deficiency of electrons that occur in a conductor, because whenever current flows, there is a bias or there's a battery that's connected, which supplies electrons, so the charges to flow, and there's no dearth of any electrons that happens. Quantum entanglement phenomena is an interesting phenomena in quantum mechanics or quantum computation that happens. It says that that the two states are entangled in such a manner that they cannot be separated. Okay, so the identification is done, or rather they are written as an entangled state, and one cannot actually get an information about which are the states that got entangled, which are the individual states that got entangled, and they are they are only available in entangled form. And this is, as we have shown during the course of our lecture, that it is quite important for the teleportation. The research, the status of computing in quantum computing research in India is it's going pretty well. There are lots of places where this research is being done, but mostly the research is held at the theoretical level. We are not yet making a quantum computer, but however, the efforts are on. Many of the industries are actually coming forward to understand what is quantum computing, because there's most of the people are not exposed to this quantum mechanics idea per se, or even if they are, quantum computing is much more involved, just knowing the basic concepts of quantum mechanics. But it's coming up. A very large amount of research is done in the theoretical field. So there are lots of hurdles in quantum information that are faced. It's a good question, and in fact, one needs to understand that why are there hurdles, and why this research is not taking place at the experimental level, at the sort of the level it should happen, or it should occur, given that India has very large number of good universities which are internationally competitive. One of the main reasons is that it's extremely sensitive to the surroundings. That is, a quantum state is susceptible to measurements, and is vulnerable to measurements or interaction with the environment. So the moment you make a measurement, that state goes away, and there is no so it collapses into one of the states that it is supposed to be, one of the states that it is supposed to be at. Just give you an example of this Schrodinger's cat, that unless you have made a measurement, it is still in a superposition of dead and alive. But the moment this measurement is made, it collapses into one of these states. And similarly, so this is one of the things in a more technical language, it's called as decoherence. So this decoherence is one of the main things about impediments of quantum information. The other thing is the propagation of errors. You must have seen that while we did this small bit of quantum information during our course, we had done a lot of unitary transformation. So there are the propagation of errors that had happened, and which are not suitable for, or they introduce a lot of errors in quantum computation. So these are some of the main impediments. So why do we consider complementary parameters in the unitary principle, Heisenberg's, uncertainty principle, you mean to say. Uncertainty principle, yes. So uncertainty principle or the Heisenberg's uncertainty relation actually has the canonically conjugate variables inbuilt into them. So this happens, the simultaneous measurements of X and P are only debated about in the principle, and one doesn't talk about any other quantities. So there are three canonically conjugate quantities that we are aware of. That is the X and P. So delta X, delta P is of the order of H cross or H cross by 2 or whatever you say. It's the minimum value is H cross or H cross by 2. And E and T, energy and time, and also angular momentum and the angle. So these are talked about. Symbolic math toolkits viable for providing proofs. I am afraid I don't understand the meaning of it. But if you're talking about symbolic maths toolkits, they are not viable for providing proofs, but they can make life easier when you try to derive something. So decoherence and wave function collapse are taken in the same spirit. So when you make a measurement or a system, a quantum state or a state function interacts with the surrounding, it collapses into one of them, one of the available states or one of the eigenstates of the problem. So, and that's why the decoherence occurs. So the decoherence and wave function collapse are taken to be synonymous with regard to the impediments of quantum information that we are talking about. Wave function collapse is deterministic and required at the point of measurement. Decoherence is inherent loss due to length scale. That's true, but we have just used it in the sense that we have talked about when there are, so this was actually talked about in the context of what are the main problems or what are the main impediments of quantum information, and in that sense this wave function collapse was taken, which happens when the measurement is done, and that's taken to be same as the decoherence problem. So to a certain extent you're correct, because decoherence means that it becomes it's inherent, and it could happen to not only because of length scales, due to other reasons as well. But here we are talking in that context, that there's wave function collapse and decoherence to be the reasons for quantum information to have difficulties. How can we consider creation and annihilation operators or operators which add and remove photons in quantum optics? Right. So it's very important to understand that the quantum optics, or rather this, the whole thing is based upon harmonic oscillators which have linear dispersion. That is, it goes n plus half h cross omega. It's linear in L, so they're equally spaced. And when they're equally spaced, one can actually have operators to create and destroy. So as if in n plus half h cross omega, there are n photons or n oscillators that are there, and so that's the reason that one can actually destroy one state and go to one state lower, or create one photon or one oscillator to go one step higher. Yes, the de Broglie wavelength of photon is what I just showed. It's lambda equal to hc by E, where E is the energy of the photons. E is the energy of the photon. So that's just been discussed just a while back. Can we derive Newton's law by, or derive, you mean to say? No, I mean Newton's laws are deterministic. Whereas the Schrodinger equation, first of all, Newton's laws are time-dependent equations, and these are written down and solved to find x as a function of, or the position of the particle as a function of time. whereas the Schrodinger equations are written down to solve for the wave functions, mod square of which give the probability of finding it at a place. When decoherence happens, target and observer is combined or entangled. How can you compute the overall wave function? In fact, you cannot. The overall wave function is not, it cannot be computed because it has the state function, the very fact that it's a quantum state which has multiple possibilities of being in any of the available or its accessible states, that is not there. Decoherence measurement, not too sure, but yes, there are measures of decoherence. What are you talking about deriving? You're talking about deriving Newton's laws from Schrodinger equation. No, they cannot be derived. Superconductors in quantum computing. I think this is this will get very technical and how superconductors and they are actually there are superconductor quantum interference devices called as SQUIDs, SQUIDs, and these are the ones that are that have relevance to quantum computing. It will require a lot of time in order to get the idea across. We'll skip it here. But will the level of the written exam be similar to the to that of the assignments? Yes, it's a good question again for everyone. The final exam would concentrate a very large part on the assignments, which means that there will be questions which are pretty common and in spirit, in the sense that the ideas, etc., the concepts would be very common to the ones that are being asked in assignments. So please prepare them well. This is, of course, as I said, that the name suggests that it's an advanced course on quantum mechanics. So it's bound to get a little tough. I'm sure that you would be able to cope with this. The quantum cryptography, I cannot do it. In fact, I had plans, but however, being an 8-week course, we had to stop short of doing only the entanglement and so on. A little bit of things, the cryptography, and there are some algorithms which I wanted to do, which could not be done. As I asked before, please check the assignments. The assignments will be checked. I have been told to give your ID so that it can be checked once again. This is to BB George Francis. So let me take some more questions on this. Somebody asked this question that conservation of charge results from gauge invariance, and from which invariance do conservation of isospin, charge conjugation, time reversal, baryon number result from? That's a fairly technical question, but we did not want to go beyond I mean, just the time reversal invariance and the parity and the rotational symmetry. I'll get this electron affected due to gravitational force. Just a moment. So what happens is that isospin is because of a SU2 symmetry, in the sense that when you have the neutron and proton, which can be written as 1, 0 and 0, 1, they more look like the spin half objects, and which has a SU2 symmetry. So this is a SU2 symmetry, and of course there are SU3 symmetries also where there are UDS being considered. And the charge conjugation is a symmetry of electromagnetism and strong forces. The time reversal, of course, per se, doesn't have a conservation law. If a Hamiltonian is not explicitly a function of time, then the time reversal symmetry holds. I guess the baryon number conservation is more like a global symmetry. So Electron affected by the gravitational force, it is not affected, because if you write down the electromagnetic force that is acting on the electron is 10 to the power 40 to 42 times greater than that of the gravitational force. So while we talk about electromagnetic forces which are much greater than the gravitational force, we don't talk about that. You can do a simple-minded calculation by taking 10 to the power, it's a g m1 m2 by r square. Say you take r to be equal to 1 unit between two electrons. That's the gravitational force. You're talking about two electrons at a distance 1 unit. And if you do the same thing of calculating Coulomb's law, which are typically of the order of q square by 4 pi epsilon 0 r, so a q square would be 10 to the power minus 19, 10 to the power minus 38, whereas this m square, which come in the gravitational force, they are of the order of 10 to the power minus 62, because this m is of the order of 10 to the power minus 31. So, when we talk about charges and electrons and so on, the gravitational forces, they are not taken into account. The local charge conservation is a concept that is taken, including in in superconductors and in other things, that where locally the charge is conserved, but globally there could be a charge imbalance that can happen. Bound states are states with negative energies. So when you solve a Hamiltonian, suppose the Hamiltonian is to be solved in a region which has negative potential, then the particle will get bound, which means it will have energy lower than 0, and the states will be not extended states. These are bound states which have the form, say, sine hyperbolic or cosine hyperbolic or exponential minus kx kind of form, not exponential ikx, which is an oscillatory solution. So physically, if you want to visualize what a stationary state is where the probability of finding a particle remains independent of time. So it's a state which exponential I omega t, and so that you take a mod square of that, the time dependence goes away. So it's just that the time becomes coming in only in the exponential I, so that we don't have any this thing. Use of advanced part of quantum mechanics in high energy physics, very much there. A lot of high energy physics requires an in-depth knowledge of quantum mechanics and advanced quantum mechanics. Yes. All right, I will give a small gist of quantum. I'll try to give a small gist of quantum cryptography, or at least give a good reference where you can get it. Charge, of course, less than electronic charge. The quarks have charge less than electronic charge. It's a fraction of the charge. Potential step, right. So what can happen is that if there's an electron that is coming from a metallic region, metal means where the energy levels are infinitesimally close to each other, and it's made to incident on a barrier which is at the interface. On a interface, and there is a barrier that is there, which means that there's an insulating region. So from metal to insulator, it will experience a step or a potential, which is potential discontinuity, which can be looked upon as a this potential step in a physical way. HEP would be more towards particle physics and thermodynamics. Of course, HEP is a high energy physics, which requires a lot of phenomenology and the knowledge of standard model, which of course we haven't talked about. Fractional charge particles are, of course, one finds it in the not only in high energy physics like quarks, etc., but also the fractional quantum Hall effect shows existence of fractionalized charges. Electron is, of course, bound to the nucleus, but if you can give an energy by which it will go out, or it can sort of be ionized, if you give enough energy, it will ionize, so it will go out of the nucleus. Yeah, so right, they're not stable. I mean, it's not that the fractional things are not stable, but in certain scenario it is. But of course, there are existence of quarks that are seen. S matrix is a scattering matrix. S operator. So basically, what it means is that when you try to time evolve, you're talking about the S matrix in the. You mean the S matrix is not always the scattering matrix, but we can scattering means when we talked about scattering theory. Is that what you're talking about? If that is what you mean, then of course. The scattering. So what I have taught in S matrix, or rather, there's an example or assignment problem. It's a combination of the time evolution operator. It's a U dagger T prime that is taken as S. No, S in that sense, it is a matrix that we have talked about in the context of time evolution operators. No, I mean, as I said, that there is no decrease in the number of electrons as they flow through a conductor from a high potential to low potential. There is a continuous supply of electrons from the battery that it is there, and the battery that is biasing the junction. Nothing is showing in the YouTube screen. I guess people are looking into this. Now it's fine. Okay. Can I take Compton, photoelectric, and pair production simultaneously? I mean, they are all different phenomena. Compton is a knocking of an electron by a photon. Photoelectric is a knocking of a photon by an electron, and being essentially collected by a detector, and then pair production. So they are all experimentally seen. I don't quite understand what you mean by simultaneously, but they can be seen. So generally, a lot of questions are that what is the application of quantum mechanics in industry? As I said, that the nano science and nanotechnology all require the knowledge of quantum mechanics. And that's because the world is quantum at very small length scales. So when the energy levels that we talk about of particles, that is separated at least by h nu or h cross omega, that energy scale. So when h cross energy scale becomes important, then of course the quantum mechanics takes over and becomes more important in classical mechanics. It doesn't have to be a microscopic system. For example, the superconductivity is a quantum phenomena which shows up at macroscopic scales. But yes, in general, all the quantum mechanical phenomena that happens in microscopic and subatomic levels, which are quite apparent, that their energy levels, like say you talk about a hydrogen atom, the energy levels are minus 13.6 electron volts, the ground state energy, and minus 3.4 electron volt is the energy of the first excited state. So there is, of course, a very large difference. And as you go towards the towards zero, that is, go towards the extended states, it becomes closer and closer. But still, it is still at of the order of h cross omega or h nu, so that we have to use quantum mechanics. The pair production happens in free space. There's some thing to do with the energy and momentum conservation. Non-linear algebras, don't exactly know what you mean by non-linear algebras, but if you mean I mean, of course, the linear algebras are most important. The non-linear algebras may find some use when you have when you are actually perturbing the system with large fields. In black body, whether all oscillators are oscillating with one frequency. No, they are not oscillating with one frequency. There's a spectrum, there's a distribution of frequencies that they are oscillating with. Energy scaling, it is done in order to compare between two physical cases. Sometimes the energy scales are different in two different systems, but the scaling is done in order to establish a correspondence between these two systems. So the scaling becomes important in most of the time. Especially in statistical physics, there's a very large importance of energy scaling, which gives a handle on understanding the order of the phase transition or the universality class of the phase transition. What's the full question in free space? Okay, so there's a question to this. In context to this, probably the pair production. I guess most of you are students in different places, and a little more, sort of questions that are relevant would be very helpful for you. I mean, if you ask something that are important for your concepts and all that. Go ahead. A Hall effect is the phenomenon that happens in a two-dimensional, essentially a two-dimensional material, when you pass current in one direction and there's a generation of voltage in the other direction or across in the transverse direction. This was discovered in 1879 by Hall, somebody called Hall, and that's why the name Hall effect. However, just about 100 years later, about 1980, the quantized version of the Hall effect was discovered. Spin flip scattering refers to a potential which flips the spin of a neutron, say, for example. But there are no, at least so far I know, there are no spin flip scattering of a neutron. The neutron scattering, but they're not spin flip, unless you have some term which flips their spin. So basically, scattering is a phenomena that a neutron comes and interacts with the parameters of the crystal, the solid crystal, and then gets scattered and collected. So usually, the potential from the crystal is independent of spin. So one really doesn't see a spin flip scattering, but in some cases it could. What are the benefits of expectation values and operators in quantum mechanics? This is you're very well exposed to average values in classical mechanics, or in statistical mechanics, the ensemble average values, where the statistical mechanics works only when you have a very large number of systems or particles that are being considered. So we take an ensemble average. So quantum mechanics demands that the expectation values are taken, and this every observable is associated with an operator. Like if you want to know what is the energy, or what is the energy of a system, then the Hamiltonian is the corresponding operator. So every observable has an operator. So quantum mechanics actually is based on these operators, and everything that you talk about. Angular momentum, we talk about angular momentum. So it has there's an operator and there's an observable, and the observable is actually in terms of the quantum numbers. Any good thermal conducting and electrical non-conducting? I mean, thermal conducting, I mean, anything that is any metal is a good thermal conductor. Electrically non-conducting, any plastic is a non-conducting material. Not sure why the question is there, but that is there. Why the electron spin? Electron spin is related to its rotation. Very good question. This is called as the spin-orbit coupling. So the spin and the orbital effects are coupled in some material, or rather it is even in hydrogen atom, there are spin-orbit couplings. It could be very small, but they are they are connected. That is, they are linked. So there's a L dot S coupling. L is the angular momentum, orbital angular momentum. S is the spin angular. What is eigenvalues in physical? So eigenvalues are the values that you would get if you operate a state function by its observable or its operator. So an operator operates on a state function, gives me the eigenvalues, which is, if you do a measurement, you would get one of those values. The one that you get is one of the possible eigenvalues that are of a given problem. So H acting on psi gives you E psi. E is the eigenvalue of H. Fundamental distinction between wave mechanics and matrix mechanics. This is just formalism. I mean, wave mechanics is all developed in the form of writing down waves, psi xt and all that, and then you write down integration of psi star x t. Can I use the board for a moment? So you can write down a psi star psi dx, or you can write down a psi star h psi dx or dv. I'm writing in 3 dimension. So this is basically how wave mechanics develop. And then with this Dirac's Bra and Ket algebra coming in, you can write this thing as psi psi, and this as psi h psi. Remember that each one of these psi is a column vector. So it's a vector like this, which has entries here, 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 and so on. And H is actually the Hamiltonian of the system, which has a matrix form. So it's essentially, a matrix that is that has to be taken. So there is a psi which is here, there is a psi which is here, and when you take this, you actually talk about numbers or the expectation value of H. So where psi 1, psi 2, etc. will be written, and where psi 1, psi 2, etc. will be written. And so these are elements of H. So each element, so if I take a psi 1, H, psi 1, it will give me some one matrix element, H11, And similarly, I'll take another one, H psi 2. It gives me another H1 2, which I can write it here, or I mean, it can be written here, here. Whatever. I mean, H21 and H12 are same if it's a Hermitian operator. So basically, it's a parallel formalism, and it conveys the same meaning. A little modern is the matrix mechanics, but it just they are all both tools to which have developed quantum mechanics in a very systematic manner. So, well, I don't know what new to say about the wave function, but wave function is it by itself, it doesn't have any physical significance. But when you take a mod square of it, it gives you the probability of finding a particle. So a psi square integrated over all space will give you 1, which means you have to find the particle somewhere. So that's so psi has certain properties. One is that it is square integrable, which means that the mod psi square dx or dv, whatever, over all space, it gives you 1, and it's properly normalized so that we can work with it, and it's a very it gives you the same information as one can obtain by solving, maybe the x as a function of t in classical mechanics by solving Newton's laws. So it doesn't give you directly the position of the particle, but the probability of finding it. The conjugate of the wave function is psi star. So it's basically just now, if you have observed what I wrote as a horizontal vector, that's called as a conjugate psi, and conjugate of the wave function. And we use it to take we actually have to find, when you find the eigen values or expectation values of certain operators, we operate that on the wave function, and then we have to take a conjugate of that and squeeze it between the states in order to find the expectation values. Mod psi square is related to probability. Mod psi to the power 4 has no meaning. It is only that there's no y. Mod psi square dx is equal to 1. There's no to the power 4. Doesn't exist. So the wave function is a square integrable. It's not integrable when it's to the power 4. I cannot answer that question. What's the value of the certificate? You know it better than me. Good reference books on advanced quantum mechanics. Sakurai is a good book. Marsbacher is a good book. These are two good books that are that you can find. But however, only after you have gone through a book like Griffiths or some other book that is that's more understandable. But Sakurai is a good book if you want that. Why we take wave function for what? You have to ask that question. Wave particle duality implies uncertainty principle as vice versa. Wave particle duality probably can be connected to the uncertainty principle, but the concepts behind them are quite different, in the sense that the main things that they stress on, wave particle duality says that every particle has a wave description, every wave has a particle description. So if you're seeing a wave in quantum mechanics, there must be a particle associated with it, and vice versa. The uncertainty principle talks about the uncertainty in conjugate variables in their measurement. Okay, so when you do a measurement of, say, P, and if you want to make it precise, want to make a precise measurement, then you have to give up a precise precision in measurement for the space variable X. Okay, so there is the way they came up are quite different. Fourier transform, I mean, the Fourier transform go from one space to another. Yes, Fourier transforms have a role in uncertainty principle, in the sense that if you want to go from X space to P space or X space to K space, you do Fourier transform. And these variables X and K, they are related by the uncertainty principle. They are related. So there's a relation between the Fourier transformation. Fourier transformation takes you from one one canonical variable to another canonical variable. Okay, and Fourier transformation is done in classical mechanics as well. But this thing, that uncertainty principle, is very selective. Rather it pertains to only quantum mechanics. Powell and Krisman. Powell and Krisman is a decent book, old book. There are many modern books that have come up, but it's a good book, Powell and Krisman. It's a good one. Thank you very much.